Right. This better? Okay, good. Thank you. It's a pleasure to be here today, and thanks to the organizers for inviting me. So I'm a bit of the ugly duckling here today. I know nothing about your domain, as I'll explain in a bit, but I'm coming more out of the HPC environment. So I'll talk a little bit about HPC today. So high performance computing is what it stands for, or large scale computing, and I'll talk a little bit about what's happening at a European scale. This is the program. I think it's fantastic, the program today. Many good teachers for you today. So really use teachers out there. If you have more technical questions about the infrastructure, please also approach me. I'll be here all week. So don't be afraid to approach me. Outline for the talk today, I'll spend about 30 minutes doing a bit of introduction, then a bit of compute architecture. Yeah, a bit closer. All right. Then on large-scale computing services, which kind of is like a generic term for supercomputing, which is traditional high-performance computing, high-throughput computing, or HPC, and cloud computing, and then a bit about Europe's digital transition. So what's happening with the European data spaces, with simple EuroHPC and Destination Earth, to give you some examples there. Introduction. So I made sure to wear exactly the same shirt as in the picture, so you can find me later. The glasses are the same too, actually, but it's not in the picture. So I was not allowed to wear them. They were too dirty at the time. All right. So I'm a senior advisor at SURF, and my background is more in astronomy. So I did a PhD at Leiden University in the Netherlands, and my postdoc was also at the university and also in the Netherlands Astronomy Institute for Radio Astronomy, so Astron. So completely outside of your domain. My satellites are pointing away from Earth and not towards Earth. But during my tenure at SURF, I've also gotten into some Earth observation applications and some projects. So I think I know a little bit of what you're doing. My research at the time was in astrophysics and intergalactic medium. So that's all of the tenuous gas between galaxies. Nowadays, I really work on high throughput computing. So anything that has to do with petabytes and exabytes of data. So Copernicus is slowly moving into this regime. And European projects. So European Open Science Cloud, as Milutin already introduced, the Green Deal data space that we are establishing, and other projects like C-Scale that are working in the European Open Science Cloud. And C-Scale stands for the Copernicus EOSC Analytics Engine. So a bit about SURF. So SURF is a national organization for IT in the Netherlands. We work with academia, so education and research. We have about 100 members. We are a service provider, so we provide high-performance computing, data storage, etc. We're also an innovator, so we work with emerging technologies. We try to push digital transformation. We share knowledge. That's also why we're here, sharing expertise. And our main goal is to accelerate the goals of our members via IT collaborations and services. These are the types of services that we offer. So we have about 8 categories. We have over 50 services as a national provider. This week we'll focus on the compute services, but we also do data, network connectivity, infrastructure as a service, so that's cloud and virtual research environments. Security, trust and identity, very important these days. So how can you also securely work on these systems? Digital platforms of all kinds. We also do agreements with market parties. So for our researchers, when they want access to public cloud, we can offer that at a reduced price, for example. And of course, expertise, advice, and training. That's something we really work a lot on. And in the picture, you see one of our tape libraries for long-term preservation of data. And we have multiple locations throughout the country to make sure that the data is safe. So not just one, very safe. There is a disaster, you lose everything. Everything is replicated over multiple distributed locations. So before I go into architecture, who of you have ever worked on a supercomputer? Just show of hands. Okay, quite a few. That's nice. I won't have to go too deep. That's nice. Thanks. I'll do a very brief introduction to high-performance computing. So at a high level, ask me questions anytime if you want. And like I said, I'm also here all week. Very briefly into the definitions. I'll just stick to the CPU. I won't go into GPU accelerators and those things. A bit of parallel programming. Very hint at how you can run jobs and what is needed there, but your teachers will show you more when you start to work on the infrastructure. The hands-on exercise, of course, you'll get later in the week. So high-performance computing is what? For example, processing of data from satellites. That could be high-performance computing if there's large data streams. Simulations, molecular chemistry, for example, also require very big calculations to ensure that things are working properly. And in essence, when you say, okay, high-performance computing is what? It's an area of computer-based computation that includes all the work that requires a high computing capacity or a high storage capacity. So typically for me, it gets interesting when you are above, say, the 10 terabyte level, and you need more than 100,000 CPU core hours. That's when it starts to be interesting, because then it does no longer fit on a laptop. It's really meant, these infrastructures, for running parallel processing of advanced applications and do that efficiently, reliably, and fast. And we have advisors like we have at Surf around to help you researchers trying to move those kind of applications you have into this parallel world. We also basically try to orchestrate compute power in such a way, through schedulers, through different ways of working with the systems, so you can get many jobs running at the same time and hence achieve a higher performance than your typical desktop. And of course, we have to see how your application will actually fit. So very brief, what is a CPU? Well, you kind of see it here. It's a control unit with an arithmetic unit. It goes over a bus to a memory to try to fetch the data, and that data is coming out of what we call the peripherals, which is input and output. And of course, the whole thing is run by Boolean logic, so zeros and ones. What does it actually look like? So this is an old-fashioned CPU, Intel Sandy Bridge. It was already old when I was young, but it kind of gives you a bit of an easier example of looking at things. So there's only 4 cores that you see here in the picture that try to apply instruction sets to your data. The data is coming through the shared L3 cache via the memory controller, and of course you have processor graphics and also some additional memory controllers for displays in there. So this is what an actual chip would look like. Nowadays the chips have many more cores. Up to 192 cores are already available, and we expect 256 cores coming soon on a single CPU. This is what it looks like if you are a technical engineer or electrical technical engineer. So you have registers, instructions. I'm not going to bore you with all of this, but if you really want to understand how it works, you need to understand this level of detail. So how do I really efficiently move data through my CPU or a different type of accelerator like a GPU? And these things are changing fast. So for a long time, we were all standardized on x86 type architectures. That's what you have. Well, nowadays, actually, you don't. If you have a Macintosh, you're on an ARM. But in the past, let's say a few years ago, it was all x86. But we're really seeing now a change, an increasing complexity, CPUs, GPUs, other types of accelerators in network computing. And in order to use those devices efficiently, you really need to start having more technical details again. So if you want to make efficient use of modern infrastructures with a diverse set of technical components, you again need to spend more time on looking at that infrastructure, see how can I map this to my problem and how can I make efficient use of all these components. But luckily, you have people like me that can try to help you with that. So yeah, don't be shy. What is a larger computer actually? If you look at CPUs, well, we have lots of servers with CPUs. They have all of memory. And if you really want to do a complex problem like a simulation, you want all of these CPUs and all of these jobs talking to each other over a very fast network. And this network is typically an interconnection network. So, for example, InfiniBand is a well-known interconnect between servers if you really want to do a complex simulation like a weather forecast. Of course, nowadays we also add other accelerators to the problem. So GPUs, for example, are very popular. But in order to really understand how to use those, you already need a bit more information. These typical GPU has a lifetime of 2 years only. CPU 4 to 5 years maybe. And these technologies change a lot from generation to generation. So each time you have to remap your code. So if you go back to what is large-scale high-performance computing, well, it's the part of computing focused on making computers collaborate effectively and efficiently, both hardware and software, up to very large scales. So, the largest type of supercomputers these days, it's a football field full of servers. For example, if you think about the EuroHPCs, I'll go to them in a little bit. Those can do exaflops, and I'll tell you what an exaflop is in a bit. Like I said before, the diversity in architecture and optimization is also increasing very starkly at the moment since about 2 to 3 years ago. So you really need to dive a little bit deeper if you want to make your code run efficiently. And in fact, if you take a code you wrote 5 years ago, and you look at how it performs on different CPUs, different generation CPUs, it will decrease its relative performance if you don't change your code. So each time a new generation CPU comes out, your code will perform a little bit better, a little bit less good per core. Overall, it will still improve if you can use many cores, but the per core performance is going down on average if you don't modify your code. So what has happened with the computers in general? So this is just the Dutch national supercomputer. In 1984, we could do about 0.1 gigaflops, and I'll tell you again what a gigaflop is in a little bit. And nowadays, well, actually, this is 2023, that we were at 18 million gigaflops, and we are actually moving now towards 25 gigaflops or 25 petaflops. And you see a Raspberry Pi was already nowadays is 2016 was 0.4, so it was better than a supercomputer in the late 80s. And probably your mobile phone nowadays is like a Cray in the 90s. So it's going fast. Just briefly on running jobs. So this is the type of system you're getting access to, schematically represented. So you will log into the system from your laptop or your desktop, wherever you are. And you will enter the system over the internet. You go to a so-called login node. Typically, we call this a UI, which stands for user interface node. From that node, you have access to what we call a batch scheduler. So that's just the system that tries to schedule your job, your work, onto the compute architecture. And the compute architecture is the compute nodes that you see there in the bottom, which are basically designated by WN, which stands for worker node. So a node that does work for you. These are all connected over shared file systems, which in your case is based on ZFS on the system you will access, which is a particular file system which is meant for data availability. You can also have choices in different file systems on your different supercomputer, for example. Some have file systems that are very good at calculations, others are more suitable for data availability. And that has to do in the end with the speed in which you can run your computation. And of course, you can work with external storage. So if you move your data from your laptop to the system, then your laptop is an external storage space, basically. And you move it onto the shared file system where you prepare your data for work on the system. And the axes here between the nodes show that you could have an interconnect. Now, the system you will have will not have an interconnect in this case. You will have a single node and a few GPU nodes that you have access to, so no interconnects in this case. But if you are interested, then let me know. I can tell you more about interconnects. Again, the practical exercises will tell you more about how to run jobs. So this is what the schedulers do. So I'm not going to go to this entire slide, but the batch scheduler that we'll use on the system you have access to is called Slurm. How many people have heard about Slurm before? Just a show of hands. Okay, good. There are some people around and we can help each other. Nice. There are some guides here on the link that's given, so slurm.scatmd.com. It will have a lot of information there. It's probably easier if you ask me or one of your colleagues if you don't know first before you start reading this entire thing. But it will, if you do read it, it has some commands like here. So sbatch is how you submit your job to the scheduler that will then arrange for the job to run on a worker node. SQ will tell you what is happening in the queue, how many different jobs are in the queue before you and how they're prioritized. You can look at individual jobs for SQ or all the jobs for you as a user. You can cancel your job if you think, okay, this is not going to work. I don't want it in the queue, cancel it with scancel. And with scontrol show job, you can find an estimated job start. You can also do scontrol show node. It will tell you a little bit about the different worker nodes that are available to you and what their layout is. Okay, then let's get into the types of what I call large-scale computing services or high-performance computing. So they are per definition complex. We are aggregating many different types of servers, sometimes also heterogeneous servers, and put them in a single system. So why would you really consider using this? Well, some problems do not fit on a single machine. Time to result, if you do it in a serial manner on your laptop, may take years. So, that's not nice. You want to finish your PhD probably on time, so you can't spend 10 years on a single problem. Shared systems, maybe many people don't know this, typically have a better utilization. So if you have a bigger system with more people working on it, it will probably be utilized more effectively than a single system. So you should imagine that your laptop is probably on and working on average 10-20% of the time. Your local cluster, maybe 30% of the time. These bigger systems are typically have a load that 80% of the time they are doing actual work. So that means they are not idling, they're not wasting energy as much as other types of compute may do. And of course, expertise and knowledge. If we all share the same system, we have a critical mass about discussing the problems on these systems and trying to optimize them together. So if you have many people talking together, you find faults, you can discuss optimizations, and you can do this much more effectively than if we all have our own little piece of heterogeneous hardware. And finally, for those of you that are interested in investments, procuring bigger systems, you get a better price, basically. So the more you invest, the cheaper the price per server will be. So that's another reason why you might want to bundle all this. However, of course, if we buy a single system, it has lots of features, but fitting your problem then may be challenging. So if you're coming out of something that you programmed for an ARM processor on your Mac, and you have to go to a Linux system, and you have to go to many nodes, this can be challenging. And this is where I think in most of your countries, you have a national IT ecosystem, national IT experts, they can help you. For Dutch people, Surf can help you. And this week, Surf can also help you, even if you're not Dutch. So a traditional HPC, most people then mean supercomputers. A supercomputer is a type of computer where it has a high level of performance compared to a normal computer, and you measure this in so-called floating point operations per second. Whether flops is still the right unit to go for or not can be debated, but there are many organizations around the world that like to have the highest flop number because then they're the best and the greatest. Doesn't necessarily mean they're the best at solving your problem. So flops is not necessarily, more flops not necessarily better for your problem, but it does tell you about the scale of the system. Nowadays, we measure in petaflops, that's 10 to the 15 flops, or exaflops. So the biggest systems in Europe that we're building now, and I'll get to that in a second, they are aiming for exascale systems or exaflops. And that's really when I say you have a football field full of servers. That's 10 to the 18 flops per second. Also good to realize is all of the world's fastest supercomputers run on Linux-based systems. So when I started in astronomy, it was not allowed to have Microsoft anymore or Mac OS. You better learn Linux well, and you have a head start. Understanding the shells, understanding how you work with these different systems. So if you have already know Linux, you have a head start on using the big systems. The defining aspects of a traditional supercomputer is the interconnect. So it was really meant to optimize large-scale simulations, and it will use the interconnect like an InfiniBand setup through massive passing interface or MPI type of codes. Now, it's not easy to make those types of codes, so I don't think we'll dive into those in detail. That's, you could do your entire PhD on a single MPI code if you wanted to. They can be extremely efficient, but also extremely hard to do. And they're really meant for complex, tightly coupled calculations. So where one job really depends on the output of another job. And they all kind of like have this cross-mesh dependence on each other. My personal expertise is more in high throughput computing. So that's the use of many compute resources over long periods of time to accomplish data-intensive tasks. So often semi-continuous data streams. So when you are reducing continuous data from, say, a Copernicus satellite, you want a reliable system that churns through this data and maybe also does some simulations on it in parallel along a long time, continuously all the time in an efficient and reliable manner. That's what we call HPC. And we also try then to find a system which is reliable as a whole when each component can be unreliable. So we often talk also about distributed computing then. So you may have a computing center in the Netherlands, you may have one in Austria, you may have one in Italy, and they all have components, and some of them will fail at any point in time. And so with HPC, we try to find such a way in which, if one site is down or one node is down, it will get rescheduled on another one, and you still get all your work done. One example of HPC computing is grid computing. Has any of you ever heard about grid computing before? I expected so. Good. I won't go into detail, but grid computing is one of the more popular ways of using HPC. And it's what we call embarrassingly parallel or loosely coupled tasks. So when you have many independent tasks, so let's say you want to reduce many observations from Copernicus, but each task or each observation is independent from the other, you can very efficiently scale this using HPC methods. So you say, okay, I sent this job to Italy, I sent that job to Austria, I sent that job to the Netherlands. They have nothing to do with each other, but I still want the result very fast. And so this is one way in which HPC can really help you. And finally, cloud computing. Of course, many of you know this. It's been very popular in Earth observation. My definition here is that it's a network of remote servers hosted on the internet to store, manage, and process data, rather than a local or a personal computer. Now, that definition is not that different from an HPC or an HTC system. Those are also remote servers. So what makes cloud different? Often cloud is different because it's virtualized. So it uses a virtualization technique to take a subset of your physical server and make that piece available. Why is that interesting for a provider like myself of resources? Because I can easily switch between the resources. So if one virtual machine or a container dies, I can make another one and give you that one. So it's a way of provisioning and offer resources to people. Now, of course, there's public cloud and there's also academic or private cloud. I tend to discriminate in such a way, and this is also debatable, but public cloud is basically where you have a demand-driven solution. So you have infinite resources, and you can always get a resource. And the pricing actually takes it into account if you were to buy it. private cloud or academic cloud often have infinite work to schedule, so it's capacity driven. And it doesn't have enough capacity to do all of that, and hence queuing or scheduling is needed. And so often in academic cloud, you won't instantaneously get your VM, especially if that VM is large. The reason we do that is because academic clouds are often, you have a limit to the amount of funding you can do. You can't charge for your resources, give it for free to research. You try to match supply and demand quite a bit. And hence it's much more, let's say, one-to-one than a public cloud would be. So this is kind of how I see the difference there. From a pure technological perspective, they are very similar. What do you have this week? This week, you will not actually have a supercomputer. So I'm sorry to disappoint you on that one. The national supercomputer was unavailable this week. So you'll get what I call an HPC system or a BET system, which is similar to the supercomputer, but it doesn't have the interconnect available. So if you were to run MPI codes, you can still run them with OpenMPI or OpenMP if you wanted to, but it doesn't have the interconnect for the optimization. So you won't really notice, I think, unless you want to run a really difficult weather forecasting simulation. It's actually a bit of a hybrid system because its HPC is built on top of private cloud. So we have our own elastic cloud at Surf, and on top of that, we then create different types of platforms, and one of them is the Spider platform, which is optimized for HPC, and we put different components together. And we can also easily clone the platform. So what cloud makes it easy to do is to clone different platforms that you make or components of a platform and put them together in different ways. And here you see how we do resource provisioning, platform deployment, storage integration, and finally user-facing utilities. This, I think, is important for you to know. So the file systems on Spider, we basically only have one I think you should really worry about in the course today, and that is the home in the project. That's one file system. It's based on what we call CEFFS, so the shared file system. It's globally mounted on all the nodes. All right, so you have your home and then you have a project folder, and below project you have 4 other folders. One is called data, software, share, public. And based on the role that you have, and I can tell you how you find your role, you know whether or not you can write to a certain folder below /project. So you can always write to share in public. The data you put in share is shared among the project members. The data you put in public is actually public, so it will be exposed to the internet with an Apache web server, so you can see it there. So if you really need to share a result with, say, an external collaborator from this course, you can put it in public. There will be a URL link that you can find on the documentation. You can tell your collaborator, hey, you can fetch my result here. The other file system that we have is a Scratch system. On the worker node itself, you can use it if you wanted to via the temp solution. I can help you with that, or you can find it on the documentation. This is really fast storage. It's about 10 times faster than the shared file system, if you can make use of it, but it's also smaller. Typically, it's between 5 and 11 terabytes per worker node, if you need to use it. And on the web page, you can find how to use it. Important point is none of the data is backed up. So when you log in, the first message you will get is, if your data is important to you, please back it up outside the system as well. This is a policy. Doing real backups of data is very expensive, so we tend to not do it. And we ask users to make sure that they have replica themselves. I will skip this for now for the sake of time. I'll go into European infrastructure and projects. This is a difficult slide. It's one that I think about a lot. But this is the European vision from a few years ago on where we want to go in the digital transformation. I'm not going to go into too much detail here, but basically they have an infrastructure layer where they want to reduce the fragmentation. So they want less systems, but they want more capable systems, and they want to federate them across nations and across institutes. They have marketplaces, as they call them, where you should be able to find data. And you have these ecosystems where data is going to be aggregated and going to be exposed to the world. Especially the data spaces here are quite important. I'll talk a little bit about those. Digital twins, Destination Earth, of course, is a very important example there. Also lots of work on high-value data sets. So public sector data is going to be made available. And of course, AI methods that are coming up. Data spaces, very briefly. There are 2 programs in Europe. There's the Horizon Europe Work Program, which is mostly for innovation, so for research. And there's the Digital Europe Program, which is more, let's say, technology readiness level is higher, so it's closer to business and commercial. Those have the sectoral data spaces. On the left-hand side here in the gray, those are the sectoral data spaces, and the green deal data space that I've been involved with is actually there. So that's a bit of a mix of academic and public sector and commercial sector. On the right-hand side, you see European Open Science Cloud, which is meant as the web of fair data for academia. So we try to coordinate academic data to be coming together and that you can more easily find it and reuse it. So it's all about fair, so findable, accessible, interoperable, and reusable. And finally, it should, of course, all work with these different types of technical infrastructure that they are being developed. European Open Science Cloud, very briefly. Again, European researchers should be able to find data in a federated and open manner. The Green Data Space will try to interconnect fragmented and dispersed data from a variety of ecosystems in Europe that has data that will support the Green Deal. So you can think about Inspire data, you can think about Copernicus data. It should bring that together. And finally, Simple is a new project which is funded by the EC, is to provide a middleware, which is kind of like a layer of software. Okay, good. A layer of software that's above your individual infrastructure, and that tries to say, how can we find an interoperability layer to make data accessible from different isolated sources in Europe in a uniform manner? So how can you find both Copernicus data and public sector data in the same way from the same portals and have standards to actually use them? And that's all going on at the moment. EuroHPC, that's the European flagship on supercomputing and quantum computing. On the right top-hand side here, you see the current systems. They have so-called pre-exascale systems. So those are systems with about a quarter exaflop. Mare Nostrum in Spain, Leonardo in Italy, and Lumi in Finland are the systems that are currently on either almost online or online. And Lumi actually had the launch of Destination Earth, which I'll get to in a second, last week. And we have two new systems, which are the exascale systems. So they are really going to try to do an exaflop. We have Jupiter in Germany, that they are currently pouring the concrete for a new data center, and Jules Verne in France. That is going to slowly get going. There are about 15 HPC centers of excellence. There are national HPC centers of excellence, serve as the one in the Netherlands, and you probably all have one in your countries. And there's lots of work being done on applications and trying to help researchers make the applications work on these types of systems. Destination Earth, I only have one slide. We could probably talk about that for the entire week. So basically, it's a key initiative about creating a digital twin of the Earth. And do so in a very high precision manner. There will be multiple digital twins that run on top of the Destination Earth. There will be one for environmental hazards. There will be one for all kinds of things in the end. It comes out of the European Green Deal initiative, and it's foreseen to at least a bulk part of that, of this destination, I should say, which is a term in EC, will run on EuroHPC. So it will need this digital twin, the largest systems in the world, to actually run this effectively. And I think academia will probably get more involved starting 2026. So it's been focusing on commercial applications first. There are some academic digital twins in preparation, but around 2026, it becomes more open for the academic world. Finally, I'm going to end with some potential misconceptions that you may have. One, the average CPU on my laptop is faster than the average CPU in a supercomputer. That is actually true in some cases. So if you are looking for a single job which uses one CPU and one CPU core, your laptop may be faster. These supercomputers typically buy CPUs one times every few years, so your laptop may have a newer generation than the supercomputer may have. The average file system response is faster on my laptop than on a supercomputer. Also true. Your laptop likely has a solid state drive, and it's likely faster than the shared file system on a supercomputer, which is based on slower spinning disks. The software I built on my laptop, say if you have a Mac with ARM, does not work on a supercomputer. Well, it's a different technology. So yes, it may not work. So when you take stuff you do on a laptop or a desktop and you want to put this on a supercomputer, you really have to think about, okay, how should I, do I have enough work to keep a supercomputer busy or part of that busy? Can I work according to the orchestration that the supercomputer has in place? And are there well-defined processes that I can use? How do I distribute my work over many cores and many nodes simultaneously? And does it fit my problem? And often, indeed, it requires a bit of technical understanding. And in some cases, and we'll go into that later this week, there are some higher level workflow engines and languages you can use to abstract some of this technological difficulty away. Things like Dask, Spark, OpenGeo, OpenGeo, and other things like you may have heard about as Toil coming out of the life sciences, Galaxy, Pegasus, so all workflow engines that can take some of this burden away. But with increasing complexity, it also becomes harder and harder for these workflow engines to take all of the technical depth into account. There's actually a nice link here from the OpenGeo about deploying Dask on top of supercomputer. It's an older one, but I think still very fun to watch with a nice video. This is something that I will not go into detail in today. I'll tell you a little bit about software packaging. If there is time and if people are interested, I can give a talk about the EASY project. It's all about modules and how to optimize compilation and packaging and distribution on different laptops and desktops and supercomputers. But it will take about 20 minutes to talk about that. So if people are interested, at some point I can give an extra talk on this. For today, I just wanted to show you that there are different ways of packaging software modules, and you'll be using them this week. Containers. Have people heard about software containers before? Like Apptainer, Docker? Okay, a few of you have. The good thing about container is that the application is shielded from the computer itself. So it will not actually directly use the file system of your computer. It will be contained within the container. And that can have benefits if you want to do certain ways and if you want to have your application also shielded from updates on the host system. So if, for example, in the past, if you had a Python application, system administrator would update Python, you would come back the next day, overnight, and all your Python stuff will fail. Well, that's not nice. Containers can help with that. Of course, you probably have learned to use Python environments. Conda, those types of things. Nowadays, on very large systems, we discourage the use of Python environments, especially Conda and Mamba and those things, because they create lots and lots of small file systems. If you put them all on the so-called shared file system, so a somewhat bigger Conda environment, like the one Milutin put at Surf, has like 100,000 files in there. If every user does that, I'm going to have 1 billion files on my file system. If you then start using them, searching through these files and those things, that system that has all these files will become very, very busy. The busier the file system gets, the lower the performance. If you all start using Conda at the same time, the performance drops to such an amount that the file system says, I'm going to basically be stopping all the reads and only doing the writes when needed. That's when you do for data safety. You prefer writes of data over reads, because if you do the other way around, your data is not safe. When that happens, when you stop all the reads, you will basically try to do an LS, a listing of files, and it will give you no response back. You'll think, hey, the system is down. It could just be that the file system is very busy and deprioritizes your listing. So there are ways around that, and especially the Lumi supercomputer has done some ways where they secretly package your Conda environment in a container without you knowing it. Though that's very advanced stuff. If you're interested in that, we can talk about that. But that's very, very advanced. But yeah, so Python environments on supercomputers, they are kind of on the way out. So please be aware of that. This is easy. I'm not going to talk about this for the sake of time. But if you're interested, we can schedule a small talk or a chat about this. What can I do for you this week? Well, I'm here all week. I can support your work on Spider. So I'm here, ask me questions, don't be shy. I can also try to analyze your research problem and see whether it might fit on a supercomputer or not. That's my main job in the past. This really requires a dialogue. It's not something I can just tick a box and just say yes or yes, no. I need to really look in more depth into your problem and say, okay, how could we segment the problem? How can we distribute it? What can we do? Does it make sense? If you're interested in future collaborations, SURF can collaborate with you in European Commission funded projects, EuroHPC, European Open Science Lab, many other problems that are interesting to work on. SURF can innovate with Dutch resources and also international collaborators on a variety of things like high performance machine learning, emerging technologies, etc. We are the national infrastructure for the Netherlands, so we can provide free ICT resources for Dutch researchers. Those are eligible, but they can work with international collaborators on our system. So if a Dutch person applies for access, they can also give international collaborators access to those resources. And finally, SURF is a Dutch mandated member in several European infrastructures. And the infrastructure is basically an electronic infrastructure or an infrastructure that works with digital technologies. You see a few here. PRACE, for example, is supercomputing collaboration. EGI stands for, well, basically that's the European Open Science Cloud, the federated cloud part of that. GEANT, it's the networking collaboration. EuDAT works on data management at the European level. EuroHPC, I've just talked about, is doing the new exascale computing and pre-exascale computing. European Open Science Cloud, Web of Fair Data, and Gaia-X is a bit of a commercial initiative, also trying to standardize cloud algorithms and paradigms in Europe. With that, feel free to ask me any questions. Thanks.
If you have any questions, please go ahead. So you can use this button here. So then we have also recorded question for online participants. Yeah.
I'm curious, how did you pick up the file service software? The what's it called?
CEF.
CEF. Did you do kind of benchmarking and then you said it's the best, or it's just some practical thing?
Yeah. So different file systems have different aspects. So if you think about, people may know Lustre in the past or DPFS. Those type of file systems are very good for complex calculations. So they try to maximize the performance for calculations, but they're not very safe for data. So if Lustre, if you put too much data on a Lustre system and you ask it to churn it through, it may become unstable. And what Lustre or DPFS then does, it says, well, I'm becoming unstable, I don't like it, and I may lose 1 bit of every data set. It's very bad because all your data will go corrupt if you do that. And that has happened to supercomputer centers and also local centers in the past. CEF is chosen, it's slower than the Lustre DPFS, but it's chosen for data availability. So it always prefers data writing over data reading. So if you push that file system to the limit, it will basically say, hey, I'm going to stop all the reading of data. You won't be able to do a listing of files, for example, but I'll make sure that all the data writing is secure. And so we look at it for how does it perform for data throughput? How does it perform for data safety? And what is the overall performance on different operations? And is that still okay on such a system? So lots of performance benchmarks and profiling on different file systems. Nowadays, object stores are coming, may replace shared file system to some extent. So that's what you are used to from cloud storage solutions. And also certain larger scale flash storage systems are coming. So also a lot of developments there in different types of storage systems. Yes, Peter.
In a similar question, but what does it mean, or what do you suggest to users that that run some jobs on the cluster for file reading? Can they use that system for reading files? Because when you say that writing has priority and maybe there can be some hiccups maybe, or something that are delayed for reading, what is the consequence for a job that wants to read something? Is there also an error message when something is not going? Because I ask a question, we have some problems. We have the CERN EOS system in our high throughput computing cluster, and there are some problems there that when there's a hiccup with the read, we are not notified. So it's really sometimes very problematic that you think everything went fine, but your jobs is not going well because there was a problem with the reading.
Okay, so what basically what the file system normally does, most file systems, at least shared file system, is that it'll just hang when it's saying, okay, when it's not working, basically it tries to access a file, it will keep trying for a certain while and what we call hanging. If that happens too long, you'll get a timeout. And often that error, the timeout error, is probably captured in your log file of your job, depending on what type of job scheduler and logging you do on your job itself. The file system itself will not really tell you anything, but hopefully your job script will give you an output that said, hey, error something. And that error has to be interpreted. So that's in the log files. Can you do anything about that? Not so much. Like I said, it's the overall pressure. If you really wanted to churn through data fast, then if your data fits within the local drive of a worker node, you won't move it to the shared file system. So I'll go back again to this one. So you would not move your data to the shared file system. You actually move your data to the small drives that are attached to each node. And that you can do it as long as your data fits within, say, 5 to 10 terabytes of data. We apply a scaling. So per core that you request on the system, you get between 80 and 160 gigabytes of space. So if you really want to fill up 5 to 10 terabytes, you need to ask for enough cores to fulfill that. Similarly with memory, you have between 8 and 16 gigabytes of RAM scaling there. So also ask for enough cores if you have a high memory problem. But if you do it there, you have an NVMe drive, which is 10 times faster. And if there's nobody else at that point using also the local drive on that node, then you basically can have up to 3 gigabytes a second speed. But this is the old grid model. So if your job is small enough and your data fits on a single node, you bypass the shared file system, just use the local one, but just do remember that if it's on the local scratch drive, it is scratch. So, copy your output back to the shared file system or whatever else save file system you have.
Yeah, well, we do that indeed for when we write to the fast scratch it and then we copy it after. But
Yeah.
the main thing is that the bulk of the data, like where our satellite remote sensing images, they're on the big file system, and you don't want each time to copy them over for each of the individual nodes. You want to keep them there and read them because you distribute it over all the nodes, the jobs. And otherwise, we have to keep on downloading these and copying these.
Yeah. So just to give you one idea here. So the network component of all the traditional components in computing, the network component is the one that is still improving the fastest. So at the moment, we have over terabit per second network connectivity between storage and nodes. And this will keep continuing. So copying data back and forth is not that much of a problem, but of course it's an additional action and it leads to additional fault problems. You can, of course, depending on the type of storage that you have, just open a file for reading, do a range request or full reading there, and work on the data there. However, most external storage systems like EOS will not allow a modify in place. And that means that if you want to do a modify on that data, you will still need to copy it over. If you only want to read something, then it can be done. But it really depends on the type of storage system and all the attributes that it does or does not allow. So that's, again, a fairly technical discussion. What basic technical like instructions does your storage system allow? And would you want to do those or not on data that you have in a single place? Because if you modify that file in place, the original data is lost. Probably something you don't want if it's a single copy of some valuable data. So you need to look at it in detail. What do I want to accomplish? What does my infrastructure look like? What is efficient to then do? Yes.
And do you have which solution of object store you have it? Because in this discussion, we basically use all the satellite data now in the object store, and we just do range requests directly. Yes. So, and it was quite efficient. So to bypass this problem with file system, so that would be a solution. But I'm just specifically asking about the surf. What data store solution you have? Object store solution.
Yeah. So you won't have access to our S3 storage at the moment. So we have a Swift S3 storage that is there. We also are now commissioning Ceph with an S3 backend. So we can also do the Ceph not via CephFS or Ceph block storage. We can also do object store like with Ceph. So there are many ways, basically, in the end, a storage system is a number of servers with lots of drives in there. You can manage them in different ways. And Ceph is a management system, like object store is a management system. And you try to make choices and to see, okay, what choices do I as an infrastructure provider want to offer? Object store, shared file system, block storage. And then also ask the researchers, what do you really need? And try to find a good guidance between them, to not have too many options because you have to maintain all of them, but at the same time offer different solutions for different performance problems. But in principle, we have most of them in-house. So in the end, I mean, I can tell you really quickly I didn't want to go into lots of detail, but These are, like say, some of the research IT services that we have on network, on computing, on different storage and data management solutions, and different ways of expertise. So there's lots of different ways in which you can orchestrate certain work. And that's why I say it always requires a bit of a dialogue and sitting together and thinking about the problem. And what I really think is the golden way to look at this, and this is at the top here. If you really want to make progress on performance for your application, you should sit together with as a scientist, with a software engineer, and an infrastructure specialist. If you do this triangle and you can have a long-term project, you can really make progress. I mean, we can often find factors of 5 to 10 in applications if you scale up. Any other questions? Tom.
So your work depends a lot on open source.
Yes.
Linux,
Yep.
Slurm, just to mention a few.
Yeah, those are choices.
But what do you do to return the favor?
Oh, we have, so we deliver back, to those repositories on GitHub and on GitLab to see. For example, we make applications ourselves. So we have DCAS, for example, as a storage system as well. We have one of our people that maintains the system. He does lots of bug fixes and code changes and stuff like that. So we try to, whenever we can, also give something back. But it's a very large community that we usually type into. So we typically look for open source, which has both industry and academic contributions in there. And then sometimes you can contribute. But sometimes you're also so far away from the real in-depth stuff that you're trying you're just a user in the end. But yeah, both ways. So far, open source has been quite good to us, I should say. So open source is not a bad thing. All right. If not, then I think I'll give the floor to Giuseppe, right? Like I said, don't be scared to approach me. I'm around all week.